All right. Today we are going to continue our vector discussion, but this time we get to go backwards. Okay. Yesterday we figured out component form, we figured out the magnitude, we figured out the direction. Well, what if we know the direction and magnitude? How do we write our vector? Okay. So that's where we are going to begin. Okay, so I have just a general vector up here. Let's assume that we know the direction and magnitude. Okay, how will we write the vector AB? Okay, well, let's relate this back to something that we know. To draw this vector, we travel horizontally A and vertically B. So if I wanted to solve for that horizontal component A, what might be helpful if we know the direction and magnitude?
Does it have to be something
Tangent would not be as helpful. What? Well, we'll make it easy on ourselves. We know that that's a right triangle. Okay. Um, so we have a more straight shot way than long signs.
sine, cosine?
Okay, so if I want A, which one is going to be helpful, Kyler?
That's gonna have to be cosine.
Okay, we know that the cosine of theta would need to be A over the hypotenuse, essentially. And we know that if we wanted anything involving B, the sine of theta would be opposite over hypotenuse. Well, if we wanted to solve for A, what would we need to do? Multiply that magnitude over. And if we wanted to solve for B, what would we have to do? Multiply that magnitude over. Okay? So if we want to write our vector in component form, our horizontal component can be written as magnitude times cosine of the direction angle. And the vertical component can be written as magnitude times the sine of the direction angle. We figured all of that out using trigonometry. Really basic trigonometry from geometry. Okay. And then, of course, if we wanted to write it in linear combination form, we take the horizontal component times I plus the vertical component times j. Okay, two different ways of writing our vector. All right, so we're going to do two different types of examples where we have to write a vector in component form. Okay, so here is our first example. Just pretty basic. Our magnitude is 2, and our direction angle is 45 degrees. How do we find our horizontal component? Cosine of our angle times our magnitude. What is the cosine of 45 degrees? Everybody all together. What's the cosine of 45 degrees?
Radical 2.
Okay, so when we multiply radical 2 over 2 times 2,
Radical.
we get radical 2. What about our vertical component? We're going to take magnitude times the sine of 45 degrees. Which is what, Courtney? Radical 2. So our vector v is really radical 2, radical 2. Pretty straightforward. I won't make you draw a picture every time. Just remember magnitude times cosine for horizontal, magnitude times sine for vertical. Okay? You're going to use it enough to where, well, and everything about the unit circle, right? X deals with horizontal movement, and the x coordinate is related to cosine. Okay? So anything horizontal, we think of cosine anyway. Okay? Now our next example is fun. We know that the magnitude is 3, and it's in the direction of negative 3i plus 4j. What? Like negative 3, 4? No, what I want is, because negative 3, 4 is not vector v. Okay? Vector v is in the same direction as this, but it has magnitude 3. Okay? So, what are we going to have to do with the negative 3, 4 vector? What do we need to know from that? If v needs to be in the same direction as negative 3, 4, what do we need to know about negative 3, 4? We need to know its direction angle. Okay, and how do we find its direction angle? Okay, which trig function? Okay, the tangent of theta needs to be what? Four over negative 3. Okay? So what does that give you as a direction angle when you take the inverse tangent of 4 over negative 3? Say it louder. Okay, is that really our angle? Okay, this vector is in the second quadrant. So 53.13 is our reference angle. What really is our direction? 126.87. Okay. Okay. So now we have our magnitude and direction. So now we can figure out each component. So our horizontal component is going to be the magnitude times the cosine of our direction. Okay? With your calculators, what is that? Negative 1.8. Okay. And then B is going to be 3 times the sine of our direction angle. What did you say, Michaela? Oh, yeah. 2.4. So our vector V Since we had that linear combination form in our problem, I'm going to write our answer as negative 1.8I plus 2.4J. Okay. That is in the same direction as negative 3, 4, but has a magnitude of 3. Questions so far? Doesn't it feel like we're kind of just applying old stuff to one new concept? Okay, vectors we introduced to you yesterday, but it kind of feels like we've done this before almost, right? Okay, all right. Let's make it a little bit more interesting. Now I have two vectors that I want the sum of. But the only thing I know about our vectors are each of their directions and magnitudes. Okay? Can I just add their angles and add their magnitudes and go from there? Really? You had physics, we can just do that? We cannot. Okay? We can only add vectors when we know their horizontal and vertical components separately. Okay? So we need to take each of these vectors and find their component forms and then add them together. Okay? But if you notice, we kind of have some nice angles, so this shouldn't be too bad. Let's start with vector u. Okay? To find its horizontal component, we will take 4 times the cosine of 60 degrees. And to find its vertical component, we will take 4 times the sine of 60 degrees. All right. Sarah, what is the cosine of 60 degrees? It would be 1/2. So 1/2 times 4 is 2. Matthew, what's the sine of 60 degrees? Great. So radical 3 over 2 times 4 would be radical 3. So there is vector u. Vector v. Okay. Our horizontal component is going to be 5 cosine of 90 degrees. Our vertical component is going to be 5 sine of 90 degrees.
Is the first one 0?
Yes. Cosine of 90 degrees is 0. Sine of 90 degrees is 1. So we have the vector 0, 5. Okay. So now we want the sum of these two vectors. So u plus v, when we add our horizontal components, 2 plus 0. When we add our vertical components, 2 radical 3 plus 5. Okay? If they're nice unit circle angles, go ahead and leave them in exact form. If your directions are not unit circle angles, then go ahead and approximate them with decimals. But since these were nice values we could approximate without our calculator, go ahead and just leave it like this. All right, are you ready for some physics? Okay. Yesterday, I think we discussed in here, what applications do vectors have as far as physics is concerned? Forces and one more thing. Starts with a V. Velocities. Okay? Because technically those are like two different things, right? So forces and velocities cannot be represented by a single number. Okay, they're represented with vectors because they have direction as well as magnitude. Okay, so we are going to look at a force problem. We are going to look at a velocity problem. All right. First, we'll get the big one out of the way. We're going to look at a force problem. Okay. So two forces are acting on a machine part. Okay. So one force has 2,000 newtons. The force, that doesn't make sense. Okay. So we have magnitudes of 200 newtons and 900 newtons. So anytime we are talking about force, the amount of force that's being acted, that is your magnitude. Okay, so not 2,000 newtons is the amount of force being applied, that's our magnitude. Okay. So the 2,000 Newton force is being acted on at a 30-degree angle, and the 900 Newton force is being acted at a negative 45-degree angle. Okay. So we have two forces acting on one thing. Okay. What is the resultant of these forces? What did we say about resultant? What does that mean we're going to have to do with these two forces? Okay, we're going to add them together. So two forces are acting simultaneously. What is the resultant force out of the two? Okay, so we're going to have to add these two forces together, which means, what do I need to know about our vectors? Can I add them together the way that they are?
No, you need the components.
We need each of their components, so we need to write these in component form. So we'll just stick with the first one, we'll call vector u, the second one we'll call vector v. Will that be all right? Okay, so vector u has a magnitude of 2,000 and an angle of 30 degrees. Vector v has a magnitude of 900 newtons and a direction of, thank you. Okay, so we will start with vector u. Vector u, to find its horizontal component, will be 2,000 times the cosine of 30 degrees, and 2,000 times the sine of 30 degrees for our vertical component. Okay. Kyler, what's the cosine of 30 degrees?
1/2.
I'll let you try that again.
Radical 3/2.
Yes, radical 3/2. Times 2,000 would be?
8.
Okay.
3.
Okay. And then the sine of 30 degrees would be what, Grant?
1/2.
Okay, times 2,000 would be 1,000. Vector v. To find its horizontal component, we'll take 900 times the cosine of negative 45. And to find its vertical component, we will take 900 times the sine of negative 45. Josie, what's the cosine of negative 45? Radical 2/2. So we will have 450 radical 2. And then, Michaela, what about the sine of negative 45? But negative. So negative 450. Okay. So now we need the resultant force. Okay. Our resultant force is when we add these together. So when we add these together, we're going to take 1,000 radical 3 and add it to 450 radical 2. And then we'll take 1,000 and add it to negative 450 radical 2. Okay, that's kind of messy, isn't it?
Yeah.
Yeah. Okay. This is what I'd like to do. Oh, come on. Okay, so let me just check my mode. I am in radians. That's not good. We want to be in degrees. Okay. So, let's go ahead. What I'm going to do is I'm going to take 1,000 radical 3 and add it to 450 radical 2. Okay. And I'm going to save that in alpha A so I can use it later. A for component A, right? So U plus V, is 2,368.45, right? And I'm going to take 1,000 minus 450 radical 2. And I'm going to store that in alpha B for component B. So 363.60. Okay. What did this problem even ask us to do? Let's remember. We want the direction and magnitude of the resultant of these forces. So we found the resultant of these forces, but what do we have to do with it? We have to find the magnitude and direction. Okay, so we'll start with the magnitude. Okay, to find the magnitude of U plus V, we have to take the square root of A squared plus B squared. Okay, I'm going to save some pencil lead for you. If we just write A squared plus B squared, we have those saved in our calculator. So we have the square root of alpha A squared plus alpha B squared. So our magnitude is 2,396.19. Do we have a label for our magnitude? Layton? Newtons. Okay. Which quadrant is our vector in?
First.
The first, because we have positive for both horizontal and vertical components. Okay? So when we take the tangent of theta equals b over a, and in our calculators we do the inverse tangent, it's actually going to give us the angle that we need in the first quadrant. So our direction is 8.73 degrees. What do you think? Okay.
Do you have to subtract that when you move the 80?
No, because our vector is in the first quadrant.
Oh, okay.
Is this different than how you do it in physics?
Yeah, a little.
What do you do in physics?
Go.
Would you rather draw it out?
No.
Okay. Let's think about what the picture is, though, for a second. So here's our machine part. Let's see. So, negative 45. We basically have that happening on our machine part, right? And we have to take those two and add them together. The picture is not as big a deal to me as it is for you in physics, okay? So maybe some of you are excited about that, right? Okay, any questions on this? I know we had to do a lot of work, but as long as you stay organized, it's not so bad. I would definitely use your calculator to help you, okay? I don't want to see you round here, and then round here, and then round here, and then your answer here is going to be off, okay? The more you round in your work, the more your answer is going to be off at the end, okay? So just be careful. Use your fancy calculator to help you. All right. Okay, one more example. We talked about force. Now we're going to talk about velocity. Okay. So a gun with a muzzle velocity of 1,200 feet per second is fired at a 6-degree angle. We're doing some target practice here. Okay. Find the vertical and horizontal components of the velocity. Okay. Okay. So the gun is fired at a 6-degree angle with the horizontal. So there's our vector. And there is our 6-degree angle. Okay. Okay. Does that work for a picture? Okay. You're a policeman. I'm going to start practice. Okay. All right. 1,200 feet per second is describing the what? Yes. It's describing the magnitude. So 1,200 feet per second is the magnitude of our vector. Okay. We want the horizontal and vertical components. All right. Well, we have the magnitude and we have the direction. So how do we find the horizontal components? Maddie? Excellent. Please do that for me in your calculators. Anybody have something for me? $4,000 what?
1,193. 1193.43.
And what would our label be? Is there a label? It's actually still feet per second. Okay? Each component will still have the same label as the magnitude. If you think about it, we're taking 1,200 feet per second times the cosine of 6. So our label is still feet per second. Okay? Vertical component, we're going to take 1,200 times the sine of 6 degrees. Do those numbers make sense in relation to our picture? Okay, we're at a 6-degree angle. The vertical change isn't going to be very much. All right. Tomorrow, we'll do some work with like forces, like pulling a wagon horizontally, or like picking somebody up vertically, those kinds of things. But until then, here is your homework. Okay? Please be organized with your time. I know that there are some of you going to Lincoln today. All right? Luckily, the game is early enough to where you should get home at a decent time. But make sure you organize your time. If you're not driving, you could do homework in your vehicle. Okay?